In the previous lecture, we talked about trade-offs in accuracy and interpretability and bias and variance with a particular focus on the regression problem. In this lecture, we're going to pivot to talk about classification. So in the classification problem, y is still the response variable or the outcome variable, but here it's qualitative, so it's categorical. And C is the classifier that assigns a class C to some future unlabeled observation X. So some examples: an email can be classified as spam or not spam, or a written number could be one of 0, 1, 2, all the way up to 9, like in that zip code example. So what is the goal here? We're trying to build a classifier C of X that assigns a class label from C to a future unlabeled observation X. And we'd like to then potentially assess the uncertainty in each of these classifications, or maybe we're interested in understanding the roles of different predictors among the X variables, X1 to XP. So these goals are really similar to the regression problem goals, except now we're dealing with classification where we have a qualitative outcome variable. So here's an example. Suppose there are k elements in C numbered from 1 2 up to k. So pk is the probability that y equals k given x equals k for k from 1 to k. These are conditional class probabilities at X. So how do you think we would calculate this? When the plot, you can examine this mini bar plot, for example, at X equals 5. So I've drawn this dotted line here at X equals 5, and I've got this mini bar plot right here where you can see how many were in class the gold class and how many were in the blue class, or how many were in class 0 down here where y equals 0, and how many were in class 1 up here where y equals 1. And so the Bayes optimal classifier at X is going to be this Cx, so this function of X, it's going to be j if pj is the maximum of all of the different p's, p1 up to pk. And so you'll notice that the probability here is a conditional probability. It's the probability that y equals k given the observed predictor vector x. And so let's say we're using a Bayes classifier for the 2-class problem where y equals 1 or y equals 2. We would predict that the class is 1 if the probability that y equals 1 given x is greater than 0.5 and 2 otherwise. So what if this was our data and there were no points at exactly x equals 5? How would we calculate this? Well, think back to our regression problem. It's going to be really similar. Instead of looking at just a single value, x equals 5, we could look at some neighborhood of values or a region of values, as denoted here with the dotted lines. And so this is going to be nearest neighbor like before. This does break down as the dimensions grow, but the impact of C hat on X is less than on P hat K here. So accuracy. So if we're doing this form here, in this classification setting, instead of measuring mean squared error like we did in the regression setting, we're going to be measuring misclassification error rate. And so what this equation means is we're taking the average over the test sample. So of course we're doing this over the test sample because if it was over the training sample, then we would end up overfitting our model if we optimized that. And this I just means indicator. And so this is the indicator that yi is not equal to our predicted class. And so this is going to be this indicator if this is not true. So if yi is not equal to the predicted class, then this is going to be a 1. And if yi is equal to the predicted class, then this is going to be a 0. And you're basically, for every observation in your test data, you're either going to have a 1 or a 0, and then you're going to average across all of those to get your overall misclassification error rate. The Bayes classifier using the true P sub k of x, that has the smallest error. And some methods we will learn are going to build some structured models for this C of x, like support vector machines, for example. And some of the methods we're going to talk about are going to build structured models for the probability, the P sub k of x, like logistic regression, for example. So here's an example with k nearest neighbors. And so I've got here x1 and x2, and I've got this dashed line that classifies between these two values. And so there are two classes here. We've got the blue class and the orange class. And so depending on my neighborhood here, my size of my neighborhood that I choose, which is denoted by k, I can end up with either an underfit or an overfit line here for trying to determine where I should put this line. So here when k equals 10, this is the line that I end up with, the demarcation line. When k equals 1, I end up doing basically the most overfit possible. So what that basically means is I'm just circling each point. So I'm looking at just the one point itself, and and if it's close to, so here, like for example, I'm finding all the points that are closest. If these little tiny subdots are closer to an orange, then it's going to be on the orange side. If the subdots are closer to a blue, then it's going to be on the blue side. And I'm just looking one at a time. So I'm basically, this is the classification version of playing connect the dots in the regression problem. Alternatively, I can make my window bigger or my neighborhood bigger. So for example, k equals 100. And so that means I'm looking at the 100 closest points, and I'm finding the line based on that. And that is going to basically, in this particular case, that kind of underfits our model. So the purple line here is the truth, or the underlying classifier, and the black line is showing you where that would fall if I set k equal to 100, and over here it's showing you where it would fall if I set k equal to 1. And so this has got the same exact type of trade-off that we were dealing with in the regression problem. Here on the x-axis, as I increase this x-axis, I am decreasing I'm increasing my flexibility. So down here at the bottom, I have the least flexibility, and up here at the top, I have the most flexibility. This is 1 over k on the bottom here. And this blue line is my training error, and so it's doing exactly what we saw in the regression problem, where as I increase my flexibility, regardless of what I do, my training error is going to decrease. And that's because basically by the time we've got all the way over here to this where k is 1, we're just playing connect the dots. And so we're essentially able to correctly classify all of our training data, but that says nothing about what we'll be able to do if we saw some new testing data. The orange here, on the other hand, that's showing me how I would perform in a new data set, in a new test sample, and that's going to tell me what k I should really pick or how flexible my model should be. And so what I want you to do is I want you to look at this slide, and I've got a question, a single question on Canvas for you that I want you to answer. I want you to tell me what value of k would you pick based on this slide. So go ahead and go answer that question, and then we'll be done for the day.